The question is, how would precession cause a change in temp since the actual angle of tilt does not change? And this question was put in the comments a couple days ago of a YouTube video I made last year, How Bad Was the Hominid Apocalypse? As a lot of people pointed out in the comments, I should have said hominin. What can I say? We live and learn. And just to bring everyone up to speed real quick, this is what he was asking about. These are the three biggest Milankovitch cycles. There are many more than these three, but these are the three that have the biggest effect on the Earth's climate. The first is changes in the Earth's eccentricity. Whenever one heavy object orbits another, for example, when the Earth orbits the Sun, they never go in a perfect circle. And this is because the planet has its own gravity also. As a result, the orbit is slightly off-center and very, very slightly elliptical. As a result, there's a day of the year where the Earth is at its closest to the Sun, and another day of the year where it's at its furthest. And the thing is, those days change ever so slightly every single year. Now, I'm using the orbit of Mercury as a more extreme example, but it makes it a little more visible what's going on. As Mercury orbits the Sun, its orbit shifts a little bit, and it creates this rosette pattern as it goes around and around. In the case of Mercury, that's actually caused by general relativity because it's so close to the Sun, which has all this gravity. But on Earth, we're too far away for that to have as big an effect. So instead, what causes the Earth's orbit to shift is actually drag from Jupiter. And this runs on a period of about 100,000 years. The second Milankovitch cycle is tilt, also called obliquity. Now, as you probably know, the Earth's axis is tilted relative to the Sun, but with a period of 41,000 years, that tilt actually moves back and forth between about 22.5 and 24.5 degrees. And the last one is axial precession. Now, the Earth is tilted, but it's actually precessing, kind of like a top when it spins. And at one point, it points toward the North Star, Polaris, like we have now. But if you were to go 13,000 years from now, the North Star would actually be Vega. And that runs on a period of about 26,000 years. About 3 million years ago, the Earth entered the Pleistocene. And what this shows is basically changes in glaciation, which correspond to changes in the Earth's temperature. And during the first part of the Pleistocene, it ran on that 41-year cycle, so it corresponded to the period of change in obliquity, that shift in the tilt of the Earth. But then about 1.2 to 1.1 million years ago, for some reason that shifted from a 41,000-year cycle to a 100,000-year cycle, which corresponds to shift in the eccentricity of the Earth's orbit. And it makes a lot of sense that those two could have a big effect. The change of the tilt would change the angle at which the Sun's rays are hitting different parts of the Earth. And changes in the eccentricity would change what time of the year the Earth is at its closest to the Sun. So if it's at its closest in the summer, then more light is going to hit the Earth. Or at least hit the hemisphere of the Earth where it's summer. But what has been the effect of this precession? And would it have any effect at all? Well, back in 1983, a few nations launched a program called the Ocean Drilling Program. And what they did, they sent a bunch of these boats out with these rigs on top to take core samples from the ocean crust. And in 2007, more nations got involved, more universities got involved, and they changed the name to the International Ocean Discovery Program. And one of the sites where they took samples from was this one, ODP Site 983. And you can see it's just to the south of the Iceland coast. Here's a set of the first core sample they took from that site. And here is the very last core sample they took from it. But if you were to take that very first core sample all the way through all the other samples down to this last one, you actually get more than 9,300 testable layers of sediment. And the answer to our question, or at least part of it, lies within these core samples. So for the rest of the video, I'm going to talk about this paper, Persistent Influence of Precession on Northern Ice Sheet Variability since the Early Pleistocene. And in this study, they actually looked at core samples from 3 different sites. 983, which is up there by Iceland, this one by Spain, and this one between the African coast and Madagascar. And what they looked at in particular is a process called ice raft deposition. So we have the North Pole, which is frozen for most of the year, but during ice ages, that ice advances southward. It's a slow process that takes thousands of years, and when those glaciers retreat, that also takes thousands of years. But one thing that's great about that ODP site, number 983, is it's within the range of advance and retreat that happens during ice ages. When a glacier retreats, it starts to break up near the ends, and you get these slabs of ice that kind of get caught in currents that float up and down. And with all that floating up and down in those tides, all kinds of stuff can collect on the top of it. So when it finally breaks off from the rest of the glacier and goes out to sea, it's carrying all this detritus on top of it. And once this thing's in the ocean, it's just a matter of time before it melts. Now, one thing to remember in all this is ice reflects 90% of the sun's rays back out into space, but ocean water absorbs 95%. So all that energy coming from the sun in the form of light collects in the ocean, so it warms up. Well, when that ice raft melts, that detritus deposits onto the ocean floor, and so there's lots and lots of it at this site. As I mentioned before, they looked at all these different layers in these core samples. Now, these core samples didn't go back all the way to the beginning of the Pleistocene. They only went back about 1.7 million years. But for that first 450,000 years of samples, they found that those ice raft depositions happened very predictably with a period of 41,000 years, which corresponds to that change in the Earth's tilt, obliquity. But about 1.25 million years ago, that started to change. That pattern started to disappear until you get down to here and it looks almost random. And that's in the late Pleistocene, the last 700,000 years. So what was going on? So this wave corresponds to the change in obliquity, the change in the Earth's tilt. And this wave down here represents axial precession. So that twist in the Earth's tilt where it goes from Polaris to Vega. And what these graphs on the side here represent is how much solar energy would be hitting the northern hemisphere of the Earth at that 65th parallel where that ODP 983 site is. So from just the obliquity of the Earth's tilt, you would get a period of 41,000 years, while changes in precession would result in spikes at 24, 22, and 19,000 year periods. Well, these 3 waves here represent those 2 effects added together. And what these 3 graphs show is the expected effects from adding all those together. And in particular, they were looking at the 65th and 70th parallels in the northern hemisphere, which are all very close to that ODP 983 site. The next couple graphs I'm going to show you are from this huge figure, and I'm going to move out of the way so you can see it. And there's too much going on there for me to try to explain the whole thing, but you can see the time period here. It runs from 950,000 years ago to 1.4 million years. And what's most important in this figure is this period right here of 75,000 years, and it's a transition period. So this is the bottom right corner of that image, and right here is the beginning and end of that 75,000 year period. What you can see in the yellow-red is ice rafting deposition. And it's kind of upside down, so when you see more going downward, there's more deposition happening. The black line is the benthic oxygen 18. And just to bring everyone up to speed what benthic oxygen 18 is, there are 3 stable isotopes of oxygen that are the most abundant. Obviously, the most abundant one is oxygen 16, which is 99.76% of the oxygen that we can see, certainly the oxygen on Earth, and probably throughout the whole universe. And then there are these smaller amounts of 17 and 18. Water molecules that contain this oxygen 18 isotope are heavier. So when they evaporate, so when water evaporates off the ocean to become clouds, it's more likely to be oxygen 16 than oxygen 18. Which is not to say there's none of this evaporating, just that there's a disproportionately higher amount of this, of oxygen 16. Well, during normal times, that rainwater would fall onto the continents and then roll off onto the oceans. But during ice ages, more of that water freezes and collects on glaciers. And as a result, you get a higher concentration of oxygen 18 in the ocean during ice ages than you would during normal times. Well, because there's more oxygen 18 in the ocean, some of it gets captured and deposited onto the ocean floor, mostly as carbonate rock. This here shows the benthic oxygen 18 deposition pattern at that ODP 983 site. I've marked it in red. So the convention is to show that oxygen 18 level inverted. So when this graph is lower, this black line is lower, there is more oxygen 18 that's been deposited, and when it's higher, there's less. So in this segment from here to here, glaciers were growing. And as you can see, when glaciers were growing, there's less ice raft deposition. And then you can see here, when that period of glaciation ended, there was more ice raft deposition. A second thing you can see is that from here to about here, those periods of deglaciation and ice rafting were happening at pretty regular intervals. And you can see by the numbers, they're really close in to 41,000, that period of obliquity, changes in the Earth's tilt. But then, if you look at the beginning of that transition point all the way up to 950,000 years ago, those periods become much more haphazard. And if you look here, leading up to the 900 million year ago event, you can see that you kind of actually had a warmer period with little spikes of reglaciation that didn't persist. I need to emphasize that when we talk about deglaciation and reglaciation, we're talking about processes that are extremely slow and occur over thousands of years. So during the summer, you can see these glaciers kind of shrink, and during the winter, they would regrow. And the net difference might only be a few feet to a few miles in any given year. But these are processes that can build on themselves. Like I mentioned before, the reflectivity of ice is about 90%, while the reflectivity of ocean water is only around 5 or 6%. And on land, it's not quite as extreme, but you're still looking at land absorbing between 80 and 90% of the sunlight that hits it. So when a little bit of a glacier melts, a lot more of the sun's energy is absorbed and retained as heat. And when a glacier grows, a lot more of the sun's light is reflected back into space. So these processes create a cycle that grows on itself. And this is why just a small shift of a few degrees can have such an outsized impact on the climate of the entire Earth. Lastly, I want to look at these figures where the researchers zeroed in on 3 particular periods in the Pleistocene. This one is from the early Pleistocene. Up at the top, in purple, is the precession wave, and in green is the obliquity wave. And you can see that the benthic oxygen 18 levels follow very closely with the obliquity wave. This figure here shows the transition period. And you can see that neither the obliquity wave nor the precession wave are dominant. Instead, it's an additive effect of both of them. And finally, this would be in the late Pleistocene. You can see 120,000 and 160,000 years ago. And what you can see is the point at which that ice age ended was the point at which you had an additive effect of both the precession and obliquity waves. So based on this information, changes in axial precession aren't themselves enough to sustain ice ages or periods of deglaciation. But it creates variations in the amount of solar energy hitting the Earth during the summer in the northern hemisphere. And those changes can create tipping points where ice ages start or end. Thank you for asking that question and giving me the opportunity to answer it.